So today we're going to continue with quantum error correction. So just to recall, we've got some set of operators, EJ, which is what should we call a quantum operation, which is affecting our quantum system in the following way. So we prove that the effect of the environment on our closed system would be to take our density operator to the sum of EJ rho, EJ dagger. And then we proved that it would be sufficient to find a recovery, so we can recover this density operator rho if we have the following conditions. And the condition was if rho has rho is in the code. Code C, which means that its eigenvectors of non-zero eigenvalue are in the span of aligned in this subspace, and P is a projector onto C. Then the condition was that P EIEJ JP should be equal to some multiple of P for all. So we can correct. So if all these errors have this property, then we can find the recovery map, which will recover it. And the recovery map had a similar form. So it was, what we did is we found UI and PI such that R, curly R of rho, which was the sum of UI. Now this PI is a projector, so that its emission, the UI is a unitary. So the unitary of projectors such that this will give us back rho. Now, actually, what we did was we had the sum of DII here, and Adrian and Edgar were convincing that was actually one, and they are right. So let's just look at that first and where that came from. So we found this these P's, UIs and PIs by kind of changing the basis. So instead of having these EIs with the AJs, we found the linear combinations the effect of FIs of the EIs such that this condition held for the S, where now Dij is a diagonal matrix. And when we got to the end, we had the sum of DII here. Okay, so what we showed was this. Let me write it in. But of course, straight from this, you see that this sum of DII is 1, because if we put I equal to J in here and sum, then we get P, the sum Fi P is the sum of DII P, and this is the identity, since that's the definition of a quantum operation. Okay, so you need these things always have. So this would be the sum of EJ dagger is the identity. So we have that this is the identity, which means that this is in fact p squared, which since the projector is p, so this is in fact equal to 1, as claimed by Adrian Menger last time. So in fact it is indeed just rho. Okay, so we need one more thing from last time's, which at one point we proved the following equation, which we will need, that relates these ui's with these f's, and that was the following. So we also proved, let's put that up the top. We also proved that ui dagger pi fj, this turned out, times the, let's see what thing, is equal to dij square root di. So basically 0 if I is equal to j, and a square root of di only if I is equal to j. And we also prove this, and this allows us to prove something very strong. So at the moment, we have a recovery map on our own for this set of e's, this defining our quantum operation. But the recovery map will actually work on any linear combination, which is maybe not a surprise since we kind of saw linear combination in the last proof. Okay, and that's what we want to prove first today. So, so this will be a theorem. And this theorem is called discretization of errors. So we suppose EJ is a quantum operation. And it has a recovery map. R. Okay, so that's from the last theorem. I suppose G, so curly G, is a quantum operation defined by GJs, which are going to be, which are a linear combination of the EJs. And the idea is that we can recover then R is also recovering then R of G of rho is also equal to rho. Well, since we had that the F's were linear combination of the I's and they span the same subspace of operators, now the GJs are a linear combination of the EJs, so they're also a linear combination of the FJs. So we have the GJ is the sum of L, J, R, F, R. Okay, so it's. No, I've done it running the other way here. Let me do the other one just in case I get lost. So GR, what's J? So since our recovery map is going to be these UI dagger PIs, let's see what they do to GJ. So now we just do the same thing, but now we're going to do we're going to check to see what is UI dagger PIGR. Well, that's the sum over J of LJR. And now we can substitute straight in here DIJ squared DII square root. Right, missed out square root. So here we get, so this is 0 equal to J, this is LIR divided by square root DII square root. So now we can just apply our recovery map to G. So R of G of rho. So the recovery map was the UI dagger P PI. So it's going to be UI dagger PI. And we're summing over I, the sum of the G's. So the G on the row, remember, will be the sum over R of GR row, GR dagger. Okay, so here I get GR. I'm going to write the row as square root of rho times square root of rho, and then put the other ones going back the other way. And so now it should just be that we can just substitute it here and go for this. This is the sum over I and R. So here we have all of this here. That's just that. So this is sum over I and R of L I R over the square root of DI and square root rho L I R. And now, of course, we've got again another sum of LIR over square root of DII. And I will leave it as an exercise to you, which is just similar as I did today, just similar as I did today at the beginning, to prove from the fact that the G's are a quantum operation, prove that that implies that these L's here, this is actually equal to 1. Okay, so should be okay, so this is equal to 1. And that follows from the fact that the G's are a quantum operation. Okay, so you have to, you can kind of see it, right? I mean, if you do some G, GR, GR dagger, then you're going to get some L's and some F's. But you know the F's are also a quantum operation. Well, oh, you also have to use the facts. Yeah, but you have to. Yes, yeah, so. The fact is a quantum operation, now you just have to sum L, J, R, F, J, F, I. And now to reduce these things down, you now pre-multiply and post-multiply by P, and use the fact that P, F, so now we get P equals P squared is equal to the sum of the L, J, R, and the P, F. But we know that this P, FR, FJ, then FJ is precisely the DJJ. Okay, so, and this and type P, so this is star LJR, D. So these are then 0 if they're not the same, so then you get D, JRJ, DJJ times P. Okay, and that, of course, then implies that this thing is indeed 1. Well, this is incredible because this means that we can not only, we only need to check that we can correct some errors here. Well, we have a recovery map. Then leads us to have a recovery map for all linear combinations of these. So take the shortcode that we saw in the previous class. That means that for the shortcode, which corrects any single qubit error, which was so we saw the shortcode can correct a single qubit error from, well, the identity. So error X, Y, and X, Z, and XZ. And this, of course, is a basis. This is a basis for any one level geometry matrix. Okay, so we can then get a complete continuum of errors which are recoverable using the shortcode if it's just on a single qubit. Okay. Now there was some huffing and puffing last time when we introduced the shortcode, because we effectively encoded 1 qubit onto 9 qubits, and of course, just to be able to correct 1 error, that's a lot of qubits when we're struggling to make quantum computers with more than 100 qubits. So you don't really want to be using so many. So now we're going to get serious about trying to construct better, and I will, in some most cases, optimal quantum codes. Okay, so now the fun starts. Now we've got an awful lot of exercises. Well, I'm not with the same amount of exercises as in the other chapters, but I think it's going to take us quite a bit longer because I got carried away, and the exercise is about 3 times longer than before. So I don't know, we're going to need some more time to do this. And a lot of the exercises have to do with stabilizer codes because they are so important. So here we go. So let's just go through the basics and how we define a stabilizer code and then how we find stabilizer codes. And also how we do the recovery for stabilizer codes, which is very important, obviously. Okay, so just to recall, the Paulies one X, Y, Z form a basis for the endomorphisms C2. If we tensor together, so the set sigma 1 tensor sigma n, where the sigma I is for these moments. Then these form as the basis for the endomorphisms of our Hilbert space. Now what we're going to do, so this is our vector space, but what's going to be important for us is to consider these Pauli operators. So I should call any tensor and Pauli matrices Pauli operators. What's going to be important for us is that these Pauli operators also almost form a multiplicative group. Okay, so if we recall x, z, so recall we have various identities, but xz, for example, was, let's say zx, as you know, is equal to I times 1, I think. And etc. Right? So if we multiply these things together, then we kind of almost get a group. We've just got i's, and if you put xz, then it's going to be minus iy. So almost up to plus or minus I, or not I, we almost get a group. So we define the group. I don't know if I gave it a name, yes. So we let P squiggle to be the way to write that down, just plus or minus sigma 1 tensor sigma n plus or minus I sigma 1 tensor. So we define P to be this element of this set. So this will be the set of Paulis. But now with signs here, some coefficient in front, which is the fourth root of 1. Yeah, either plus 1, minus 1, I, or minus I. And this forms a multiplicative group. And that's it's very strange group actually, because elements in this group will elements here at least, I'm trying to think. Elements in this group will either commute or anti-commute. Okay, so the signs don't actually make any difference in the function of commutativity. So two elements of P that's easy to write it like this. So for M and N in curly E, either M N is equal to M N, or so they either commute or anti-commute. And this is true for Paulis. So it's xy is equal to minus yx, xz is equal to minus zy, x, y. And obviously they almost commute with themselves on the identity. So let's just give an example. So let's say M1 is C1 x, and we usually, when we write it down, we try and drop the tensor product sign, but let's keep it for the moment, but we will drop it shortly. Okay, so let's say this was x, z, y, and n was so for some c one such that 1, and this is equal to y, let's say 1 x. Then I claim that these two will commute. So Mn is going to xy, which is oh dear. We have to decide this. Well, you don't. The point is, you don't need to work it out because x y equals to minus y z. Okay, so to work out if this is, they both got C1 and C2. So let's just compare M and N. Okay, they both got C1 and C2, so you can forget about that. And they got x y here. On the other side, you're going to get y x. So that's going to be 1 minus. These two commute, so they're the same on both sides. And here you're going to get yx, and there you're going to get xy, so they anti-commute. So in the end, you're going to get minus 1 squared, and you get n, so they commute. Okay, without actually having to remember if it's 5 times 7 or minus 7. It doesn't matter. Okay, so just to see if things commute, you just have a look and see how many times you see different pairs of non-identity Paulies in the same position. Okay. So they commute if and only if you see different non-identity Paulies in the same position. Even number times. Okay, and when you see the identity or the same Paulies, it doesn't matter because they don't commute. So you only get the sign change when you see an XY or an XZ or less. Right. So to find a stabilizer code, what we need is a commutative subgroup of P. Okay, so it's a stabilizer code comes from a subgroup S. So let S and B subgroup B and abelian are a commutative subgroup of this code A. And the stabilizer code is defined in the following way. So Q of S, so the stabilizer code. So we need to find some subspace. Remember, our code is simply a subspace of our Hilbert space. So this is going to be the set of states in our Hilbert space. So it's going to be a set of states, set of states in our Hilbert space, such that n times for all for n. I.e., you'll often see it defined as the joint eigenspace of eigenvalue 1. Okay, so the eigenvalue is an eigenvector of eigenvalue from 1 for all operators in this subgroup S. Well, I could give an example. This I could write down in a median subgroup, and I could say, okay, so this is QS. But at the moment, we want to see, like, what errors can we correct with this stabiliser code? Okay, at the moment, we'll just be well, I'll write it down in the median subgroup, and you've got this defines a subspace in some bizarre way as the joint eigenspace of eigenvalue 1 of all the operators in S. But first, what I want to do is prove to you that this can correct a large set of errors. And in fact, the errors that we can't correct are easily identifiable. Okay, so these are they going to be in the centralizer. Okay? So let's define that. So the centralizer S is going to be the set of operators E's E in curly P such that E N N E for all N in S. Okay, so they're the operators in P which commute with all the operators in S. So observe that. So of course, since S is abelian, S is contained in the centralizer, certainly. And what we shall prove is that the ones in the centralizer not S are the problem cases. So, yeah. So before we saw with the short code that could correct any one bit one qubit operator. So it was just affecting one of the qubits. So let's just define what we mean by the weight of a Pauli operator. So for any E and P, define the weight of E, just call W2 E, is the number of non-identity ways. Okay, so the weight of, I don't know, X, delta 1, delta Z, delta 1, delta Y is 3. Since it has 3 approaches, the X, the Z, and the Y, which are not identities. And now we're going to define D to be the minimum weight of Pauli's in the centralized of S. We throw S. Yeah, it was actually completely necessary. Let's define the set of errors that we can correct with our QS. Okay, so this ED is going to be the set of E's in P such that the weight of E is less than 2. And this will be the correctable set of errors. Okay, so from here, from this, we're going to prove that there is a recovery in that. And then from the discretization of errors theorem that we just saw, this will imply that we can prove any linear combination of the errors in curly D. Okay, so that's a challenge. Now, there's something we should observe here. S is going to be subgroup of P, and QS is all the states in the Hilbert space which are of which are eigenvectors of the ms of n of eigenvalue 1. So we should not have in S anything which, so observe this, so to avoid trivialities, minus the identity should not be in S. Because if minus the identity is in our subgroup, then there are no vectors apart from the 0 vector that satisfy this. But that implies
Can you repeat that again?
that all elements of S are of the form of this form, because remember, all the Pauli's, the square is always the identity. So if you had plus and minus I here with the Pauli's, then when you square it, you get minus the identity. And the square must also be the subgroup because it's a subgroup. Okay, so it's a multiplicative subgroup. So if G is in it, G squared is in it, G cubed is in it, etc.
Can you repeat this whole thing again? Like, why is that minus I being in S so bad?
Because if you imply a minus 1 in S implies QS is 0.
Oh, okay.
Yeah, because you're going to have minus 1 times the state.
Yeah, equals the state. But then what's this about? Like, all that, what, like, why does it imply that all elements of S are of the form yada yada?
Sorry?
Like the implication, like the one with like QS being 0. Yeah, but like the earlier sentence, like it implies that all elements of S are of the form.
Yeah. So or this form, because if you had I, so if this was an element of S, then n squared is going to be minus the identity.
Right.
So if n is in S, then n squared is in S, and minus 1 is in S, and QF is trivial.
Okay, so we can't have.
So it implies we can assume all elements of the form plus or minus.
Oh, okay, because if you have an I or a minus I, you have you have to get minus I, which is okay. I see.
Right, so now what we want to do is prove our beautiful theorem. I want to give you an example. But I think I can't do anything with the example until I've done the theory. And then I'm just going to have to write it up again. So it doesn't seem. I mean, yeah, we've already seen a pair of operators which commute. Okay? So you'll trust me that I can find some operators which commute and get a subgroup. Okay, so let's do the theorem, and then we'll look at an example. So the theorem is going to be that we can find a recovery map for our stabilizer codes for all errors in this ED. Okay, so for all small weight errors. So let's just recap what we're doing here. We've got a subgroup. Then we've got looking at the elements of the Pauli group which commute with all the elements of our subgroup, and they're the bad ones. They're the bad ones. So as long as we can avoid those, so if I send ED in the way that this is less than D minus 1.2, that means that if I take EI, EJ dagger, as in the theorem, the recovery map theorem, the weight of that operator is at most D minus 1. So it's not in the centralized. Because the D we define as the minimum weight of the Pauli centralized. So let's leave that up for the moment, just so while I write up the theorem. So we can do it, yeah, theorem. It is an abelian subgroup P such that So then this ED that we defined here is going to be a correctable set of errors for QS. I.e., if we put any density operator whose eigenvectors are in this subspace QS, then this set ED will be a set of correctable errors. And the first bit of the proof I already just explained, so it's already here, so let's see if we can. So recall this D is the minimum weight, other things to centralize. So recall, let's leave that there because we'll need that. For this and this. So let's take two errors in here. So suppose EI, BJ are errors, then the weight of EI and BJ is less than D minus 1, since the weight of either one of them is less than D minus 1 divided by 2, which implies EI BJ data is not in the centralizer version test. So in fact, what we're going to do, probably I would have been better if I'd done that, is just prove that anything that's not in the centralizer of decimal tests is correctable. Okay. So this is not in it. So there's got two options. Either this error is not in the centralizer, or it is in S. Okay, so case one. If it's not in the centralizer, that means it doesn't commute with every element. So there exists an element of S which anti-commutes with this. So recall that all the Pauli operators here commute anti-commute. So we have that E by diagonal E chain M is equal to minus M EI chain delta. Now, the projector, so let's do it. Let's define a orthonormal basis. So let's say this thing is an orthonormal basis. For a package. And let P be the projector. Onto QS. So this P is the sum of the Keck bars of this orthonormal basis. Okay, so I've sum over this orthonormal basis, but this matrix, this operator here, will be projected onto QS. So this is the P we saw. This is the P we saw in the theorem with the recovery map. So what we need to show is that P, EI-EJP, is equal to AIJP for all EIJ in our correctable set of errors. So let's see that works. So we can do P, EI-EJP. Now, what is M times P? So observe M times P is the sum of M, which is the sum of since these are a basis for QS, and all the vectors in QS are eigenvectors of eigenvalue 1 for the things in S. So for all m in S, MP is equal to this is equal to this is equal to P. And likewise, that's equal to the M. If we put the M on the other side, it doesn't make any difference. Okay, and bear in mind that everything is Hermitian. Okay, so these Borel operators are Hermitian.
Wait, why do we care that M is an S? Or like, or I mean, it's just for all M and S, we have this.
Yeah, for all M and S.
Oh, wait.
Yeah, no, M has to be an S because it's eigenvectors for eigenvalue 1 is the vector of the operators in S.
Oh, right, because it's the.
Yeah,
Like,
it needs to be size of walking basis for QS, which means that n times size equals pi.
oh, okay. So we were working everything in S. Okay. Everything. Like that psi is like QS is defined for S. Okay.
Yeah. And now you can probably see what you have to do. Now you just put this together. You can put the n here because NP is equal to P, but these things anti-commute, so this is now minus P and EIG. But PM is also equal to P, so this is just minus P. And so we've successfully proved that P, EI and EJP is in fact 0. So there's our AIJ is in fact 0. Which corresponded, if you remember, to the good case for the S, no? Because then we did have a diagonal matrix for our DIJs in that case. So that's the case that it's in the centralizer of S. Sorry, it's not in the centralizer of S, but it could yet be in S. Okay, so there's two cases here, which I do admit that I've missed first time. So now we have to suppose EI dash EJ is an S. Well, if it's an S, then it's an N. Well, if it's like then what we've written here, then EI dash EJ P is equal to B. And so the I of the EJ P to P squared to P. So in that case, AIJ is equal to 1. As we've not got, it's not necessarily diagonal, of course. No. I mean, it will be, if this case doesn't occur, and there are will see examples where it doesn't occur, then of course, then it would be diagonal. Because then it would you only get non-zero here, and then PI is equal to EJ. And then this is true. This is identity, so then it is in S. So we can apply our theorem. So we can simply apply our theorem. So recovering our theorem. No. which if we take any error defined by this set of errors here, so by this EI being taken EIJ here and do your quantum operation, so take any EI here and do your quantum operation, then you can recover it. Right. Okay, so finally now we're going to get to an example. And not only will I give you an example of the stabilizer, I will show how we can correct it, and then we will build a circuit which will actually do it. Well, it's not for that, not for the code I'm going to put that. That's an exercise, but I should do a simpler one. Okay, so now the fun bit really starts. So now we've proved that stabilizers codes work, and we know exactly which errors are the ones that we can't correct. The ones that we can't correct are the ones which are in the central answer, S, not S. So as long as they're not here, we're okay. And when we generally talk about the weights, but actually wasn't necessary, we should have just done without with the stabilizers there. So here's an example. And now I'm just going to drop the tensor symbol. So this is kind of standard, so let's get used to it. So here are my first two. Let me do one. Okay, so I claim that these four generate an abelian subgroup. So let's check that they all commute. So to check that they commute, I have to go through them one by one. I take each pair and then go through each position one by one and check that there's an even number of positions where I get different non-trivial powers. Okay, so here, non-trivial. So that's 1, 2, 2. Okay, that's good. 2 is even. So these two will commute. Okay, I get a minus from here, minus from here, nothing from anywhere else, and they commute. No, that's 1, 2. Okay, again, so 2, so there's going to be minus 1 squared, and 1 and 3 commute. 1, 2, okay, so again 2, first and last position, and 1 and 4, and now we check M2 and M4. There's 1, 2, and the last 2, so that's again 2, and in 3 and 4, 1, 2, here again 2. Okay, so M1, so we can check, so verified. And from that verification of just the generators, we now know that the whole thing, the subgroup they generate will be abelian. Sorry, so just extracting. So what is S? S is the identity element. Subgroups always have a density element. Then you get the MIs. Then you get the pairs, M1 and M2. Of course, it doesn't matter which order I write this down, since they commute. So M1, M3, and you get all the pairs up until M3, M4. And then you get the triples, M1, M2, M3, M1, M2, M4, up to M2, M3, M4. And finally, M1, M2, M3, M4. Okay, so the size of S is 2 to the 4, which is 16. Okay, so you get 16 elements in this subgroup. And of course, this set of generators is not unique. You could have started off with M3, M4, M1, M2, M1, M2, M2, M3. It would also generate the same subgroup. Okay? So there's nothing special about these four that are written down here. Of course, you need to check, and we will see this later on, that they are actually, that this M4 is not already a combination of the M1, M2, M3. You might have thought you found a fourth one which competes with all the other ones above, but secretly you're already just taking an element of the subgroup M1, M2, M3, M1, M2, M1, M3, M2, M3, M1, M2, M3. And you just found one of the other elements in that 8-element subgroup. Okay, so you have to be a little bit careful with generators. But these really do generate a subgroup, I think. Well, so I can actually check that. No, it's not because we're doing examples. So it works. Okay, so yeah. I forgot to tell you how to do the recovery. So the idea between the recovery is that we have some error. So now let's do that here. So let's say we have an error. So these will be our errors. This will be x1, 1, 1, 1. Okay, so these are now, we write 1 for the identity. We forget about the so let's imagine this is our error, x1, and let's see, now this, if it's a detectable error, it's not in the centralizer of this subgroup, okay? So my claim will be, in fact, that the centralizer of this subgroup has these three. So we should be able to correct every single error of weight 1. Okay, so I claim D equals 3 for this subgroup. So if E is in the centralizer of S, so in fact, yeah, if I claim something stronger, I will say that anything in the centralizer of S has weight at least 3. Because anything in the subgroup also has weight at least 3. Okay, so there's no way to a combination. If you write down all of these 16 elements, you won't find anyone apart from the identity whose weight is not more than 3 or more. Okay, so this then is not in the centralizer. It should not commute with one of them. Okay, so let's see which one it is. It does commute with the first one, because these are all identities here, and it has an X here. So this was going to give me a plus if I try and commute with M1. However, with M2, it's going to give me a minus. Yeah. With M3, it's going to give me a plus, and M4, it's going to be a minus. Now, I can do that for all single X errors, and here I'm going to get minus, plus, minus, plus 1, 1, x, 1, 1. So the third, I'm going to get minus, plus, plus, minus. 1, 1. The fourth, it's going to be plus, minus, minus, plus. And the fifth, x. I'm going to get plus, plus, minus, minus. And now I can do the same with the y's. So the y's here is going to be minus, minus, plus, minus. In the second one, it's going to be minus, 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 plus, minus, plus, minus, minus, plus, minus, 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 and a minus, minus, plus. And finally, for the z's, what you should be seeing here is that all of my syndromes, so these are called the syndromes, this sequence of pluses and minuses, they're all different. They're all different for each different error. So in total, and think about it, because I'm not allowed to have plus, 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 plus either, because plus, 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 plus would mean it's commuted with all the different errors. So there's one of the 16 options which cannot appear. I've got 15 options left then, and I've got 15 errors, and I'm claiming they're all going to be different. Okay, so let's try with this Z111. So this is going to be, doesn't commute here, but does commute these three. So it's going to be minus, plus, plus, plus. The second one doesn't commute the second one. The third one, be like that. And it's going to be plus, plus, minus, minus. And finally, it's going to be minus, minus, minus. So all I need is to set up a circuit where I can do a measurement and get these syndromes, and then I know all the errors.
Wait, can you repeat how you get here? Like, where do you send? Like, what's the code that you send, and how do you go about? Like, why does this prove that? Like, why are we making this calculation?
Sorry,
like, why are we making this calculation? Like, what's the sort of the code that we send?
So we start with an abelian subgroup, yeah? And then we define QS to be the joint. I haven't told you how big QS is yet, which is important, of course. So QS is going to be the eigenspace of eigenvalue 1 for all n in S. Okay, so that's the first place.
Right.
So that's going to be where we map they're going to be our logical bits. Do you remember in the shortcode we had 0 logical and 1 logical? The dimension was just 2. We could send 2 bits.
Oh, okay.
Yeah. This one is also, it also has, so it will turn out that the dimension of QS is 2. Okay, I will prove that in a minute. But I wanted to give an example. And so the dimension is 2, so we can send 1 qubit of information on 5 qubits. So that's been the shortcode because the shortcode had 9.
Okay.
And in fact, because if you see, just by looking at the syndromes, if we want to correct 1 error, then we're going to get at least 15 syndromes. So we couldn't have done it with less than 5.
Oh, okay, so it's 2 to the 5 minus 1, or no?
No. Okay, that's not because we couldn't have done this with 5 because we needed the dimension to be 2. So yeah, because we needed 4 operators. Yeah, we definitely need 4 operators here.
Yeah.
If you've only got 4 here, then the dimension you will see is of 1 instead of 2. So yeah, we will see that. We can't see it.
And then the corruption is just multiplying, applying x111 as an operator to, or like what's the, like how does the message get corrupted? Do you multiply it by this operator, or?
Yeah.
And then you can tell. Okay.
Yeah. So I mean, in really we do it with the density operators, but it's the same. It's just a little bit more complicated with density operators. So what we normally do is just take the state in here. So we're sending this as a logical bit. So we're probably going to fix the bases here for QS, which will be 0 logical plus 1 logical.
Yeah.
And this will be a combination of those. So this will be as per short code. And then the error gets applied here.
Okay.
We calculate syndromes, we can find the error, and then we apply the error to recover our information.
Oh, okay.
Once we know what it is.
And the one that gives plus is just no error, right?
Exactly.
Oh yeah, thank you.
I'm trying to make pen and write. Right. So there's still a wealth of things to do.
Simeon, the third and the fourth of the set are not right, I think.
What's not right?
The syndromes for the third and the fourth of the set, the plus minus minus plus and minus plus plus minus.
Minus plus plus minus.
Like they are repeats.
Here.
For the set, not the x.
Oh, for the day.
Yeah.
Oh, you're right. This is wrong. This is plus plus minus plus. Is it like that? Yeah, because I switched the sign to the 1.
Yeah, right.
Yeah, thank you, Lakeman. Yeah, because otherwise I don't have 4 syndromes with 3 buttons. They're here, aren't they? And the ones with 2 buttons are here. 1, 2, 3, 4, 5, 6. And ones with 1 button, they're here. Yeah, thank you. Yeah, so it's a difficult thing to do without making sense. Yeah, so in fact, this then tells us that if this in fact implies this, doesn't it? Because if anything now, if you try and find something in the centralizer of weight 2, you can split it up into 2 of these. And then combining their syndromes will not give you all pluses because they're all distinct. So you see just from this calculation that we made up here, that the elements of the centralizer have weight at least 3. Okay, so I've actually proved this plan by calculating this. So then when we apply our theorem, it's sensitive recovery. Okay, well let's get a bit more practical. I'd like to go through the syndrome decoding a little bit more general.
One question.
Yes.
Can you explain what exact operations do you apply to psi in order to get this plus minus plus minus? Because in theory you don't know the x1111. You just receive a qubit, and then you apply this. But how do you apply this to the qubit?
Then Guillaume, you've convinced me that I should draw the syndrome circuit. Okay, so let's do that. Okay, and then you'll see what happens. So all we know is we've got E psi, and the question is, I mean, we don't know. Okay, so you can just prove hypothetically that if you knew what the error was, you know what the syndrome you expect to get. So this is like a lookup table here. Okay, so now we're going to show you, okay, give me the E psi, I will now design a circuit which will allow you to measure the syndromes. Okay?
Okay, yeah.
Ready? Okay, so here goes. I'm not going to do it with this code because that's one of the exercises. So I can do it with a simpler one.
Not only were they different, but the added distance from one to the other is 2, right? You can make a single change and get something else. Like that's important as well, no? And like the sequences of 4, or I don't know, never mind, because you got all of them. Never mind. No. Or it's like the sequence of plus and minus, you have to make at least 2 changes from one of those to get any of the others, or is that not how it?
Yeah, that's true, but yeah, that was just that was basically using to do things with the synthesizer. Okay, so how to calculate the syndrome? Okay, so how? Oh, got lots of ink now to calculate syndrome. Now let me draw this little circuit up here. So it's been a while since we've seen the circuit. So and then side coming in. I don't need that. Coming out, H here, and H here. Now, what happens if we calculate this syndrome? So first of all, this circuit. So we're starting off with 0 psi. And we apply how much of this? And now we do a controlled M on the second qubit if the first qubit is set. Okay, so that goes to and now we get M. And now I'm applying this Calamard to the first. Which is going to be 1/2 0 minus 1, sorry, plus 0 and minus 0. 1. Okay, so that's the result here, and now I'm going to measure on the first qubit. So that's, let's write it as 0. What have we got? We've got psi mar plus m psi plus 1 psi minus m psi. So that means that this circuit, if m psi is equal to psi, then this is 0, and this is just psi. So we will measure 0 with certainty. Whereas if m psi is minus psi, then we measure 1 with certainty. Okay, so that's just showing one particular operator. Okay. So now I want to do a syndrome circuit for a slightly simpler code than we saw before. So I'm just going to do. Oh, I've done this some wrong place. Okay. So let me just do a simple one where S is generated by M1. It's going to be M2. Okay, so what I have is I have my my coding coded onto 4 qubits. So here I, in theory, have my encoded qubit psi, but it might have been subjected to some error. Okay, so here I have E times psi, and up here, let's give us this. That's not going to be enough for me. Let's see that. So here we've got our coding. And here I put 3 auxiliary qubits up here. And now I'm going to measure these ones. So I'm going to put X here, X here. And that's going to be controlled on this first one. So what I want to do on this first one then is exactly what I've done with this M here. I'm going to measure on here. So I need, and I will need on all of them, have a mask to start them off. Oh, this pen is rubbish. Let me see if I can take the ink out of one of the others. Put in. Oh, God, I've got ink absolutely everywhere. Ah! Yeah, that was not there. That was not the closest on the. So this is basically this setup here, and we go along here, put a home line, and measure. And on this second wire, I'm going to put the second M2. So here I have X and X. I put a home line, and then I measure. And then on this third one, I think that's it. So here, coming in here, we have in theory our encoded qubit. So this has been encoded onto the code space. It may well have encountered some error. I then put it into these M's. So you line the M's up. This is M1, M2, M3. And you calculate the synchrone in this way. So let's just look at an example. Let's say suppose E was 1, 1, X, 1. Now, when it comes to the N1 bit, this bit here, E commutes with M1. Okay, so it commutes with M1. So according to here, we're going to get we're going to get E psi. This is equal to E N1 psi. It's equal to N1 E psi. So this E psi is, in this case, we will measure zero with certainty. Okay, so when we look at this register, we will see a zero. We will measure zero. Okay, because E psi is an eigenvector of eigenvalue 1 of N1. Even though it's been an error. Because it commutes with the N. And then when we come to M2, so now let's think of this, because this is just. When we come to M2, E times M2, E times M2 also commutes. Okay, so same thing happens with E2. So M2 of E psi is equal to E psi also. Same reason, but E and M3 anti-commute. Okay, these two anti-commute because he's got a Z here where he's got an X. So they anti-commute. So when you get apply M3 to E psi, that's going to be minus E of M3 psi. Psi is an eigenvector of eigenvalue in one of M3, so that's just going to be minus E psi. So here we will read 0, 0, 1. So we will read, we measure 0, 0, 1. Okay, so it's like a plus and minus, it's plus and minus. Is that good, Guillaume?
Yes. Thank you.
Okay, so some of the exercises I asked you to do, like proper big ones for, in fact, probably for the last example, actually work out basically load. Yeah, I mean it's strange as well because you can also we'll see like just trying to think if you actually need to. So that allows us to calculate the pseudo. So I think I've still got time to. So I've still got to prove to you that calculate what the dimension of Q of S is. Yeah. But while we're on syndromes, let me just prove. Yeah, so let me just do the general of what we're doing with the syndromes. So Q of S is that. Any guys who code? So suppose being a correctable set of errors has occurred. Which I don't know how to spell. On a state. Yes. So for each MJ, a generator set for S. Reflect BJ B. Okay, so this is BJ. Since everything since BJ. Okay. We know these features are plus and minus 1. Okay, so all Pauli operators either commute or anti-commute. So yeah, the important thing I forgot to mention about the last circuit was when we applied the M, did you see that the error didn't really change? It might have got changed up to plus or minus one, but it didn't matter as it went through the three M's. You could just apply the next M and you either have plus or minus what you started with, and that didn't affect your measurement. Okay? So we can go through each generator in turn. We compute. So as we just saw, we compute beta j such that this is the case here. So effectively, what we were doing there, we were doing a projective measurement with the emission operator mj. So after each measurement, we have either plus or minus e.
Wait, it's in P or in S when you have the, or no, all the polys are always anti. No, yeah.
Yeah, I'm just stating that any two polys will commute or anti-commute. So just to state, after each measurement that we saw in the previous blackboard, yeah, even if we measured a -1, that just meant it just flipped the sign. But it doesn't matter if it flips the sign. I mean, the next one might flip the sign, the measurement that matters. Okay, if it's let's see if I can see. If so, you might think, oh well, if you flip the sign, then the next one's going to go wrong because it maybe flips the sign as well. You won't see it anymore, but you will see it because just because you've got an extra -1 here makes no difference. Okay, you'll still see it flipping when you do the measurement. Okay, so it's just everything's up to date. So it doesn't matter that after the measurement that you may well have flipped your error state from E side to minus E side, but it doesn't matter. If it commutes, then it will just take this to this, and you won't notice that it was actually minus E side, not E side. Okay, so after each measurement, we can continually measure one at a time and get out our betas. So after our measurement, and at the end of the circuit, we have plus or minus E. Sorry. And we will then find the E, we're going to locate the E, and we're going to apply the E. So we identify E. E by syndrome. And then quickly add these to our circuit, and so apply E. And get up to global phase plus or minus sorry. Now, what would happen if it so happened that suppose EI and EM have the same syndrome? Now, if they have the same syndrome, they have beta j's, okay? So that means that here, in this, every time we got the same errors, we ended up with the same beta j's. So what I want to show to you is that they have the same syndrome, then they're in the central, then EIEL is in the centralized. So let's see that that's the case. So let's do let's calculate ELIJMJ. Okay, so that's EIMJ squared MJ. Now, EIMJ, if I commute this, this is going to give me a beta J MJ EI. And the other MJ, I go the other way and go EL. Oops, I was getting beta J. Beta J EL MJ. And then I can be MJ again. Recalling that these MJs, all the squares of these 40 ones, are always the identity. Well, these beta j's are just plus or minus ones. That's just going to be beta j squared, which of course is going to be 1. And here I have mj ei el. And here at the end I have mj squared, which is 1. So this is just mj ei el. Then for all j, since they have the same syndrome, that's for all j, they commute. Well, that guys, EI, EL is in the centralized. So you see the centralizers are the bad boys. So now you see why. Now in our case, we made sure that our EDs were not in the centralizer unless they were in S. So since the weight of EIEL is less than or equal to D minus 1, this implies that EIEL must be in S. And now for the really clever bit, let's say you got the wrong error. You had to have the same syndrome. The error that occurred was EL. So suppose the error was EL. So we have EL psi. We identify what we identify EI. If we apply EI, we get EI EL psi. But EALI, EIEN is an S. So psi is an eigenvector of eigenvalue 1 of this operation. And we have recovered psi anyway. And that actually happens in the shortcode. So you can actually find such errors. So the shortcode on the face of it will have entries in the straight centralizer, which actually weight 2, but they happen to also be in S. So if they're in S, they will have the same syndrome, and then it doesn't matter when the product is in S, because even if you try and apply the wrong error, you will still recover your psi. So then we give these codes a name. So recall that D was equal to the minimum weight of centralizer of S naught S if D is not equal to the minimum weight of the centralizer of S, then we say QS is impure. Otherwise, so most of the time you would expect the minimum weight to just be whatever minimum weight is centralized best. But sometimes that's not the case. For example, we will see in the exercises, for example, short code. So we haven't seen yet, the short code actually is the stabilizer code. And it's impure. Short code is impure. There are weights, there is this M in S, such that with weights M equals 2. Whereas we've already seen that we can correct errors of weight 1, so therefore the minimum distance D must be 3, whereas D is equal to 3 short code.
Is there a reason behind the impure pure name? It's a very overloaded word. Or
No, and in fact, they use it for other things as well. So no, I don't think so. I don't think it's not a very good name.
they use some other name as well, or
What?
what did you say first? Like they use something else?
Yeah, there was another name, but it was even worse. And then this was basically there's won the yeah, they're called pure and impure now. But yeah, I agree, it's not a great name. Now, what's to come? What's to come is we're going to show a very nice way. In fact, it turns out that stabilizer codes, to find these abelian subgroups, you only need to find certain classical codes. So they're entirely equivalent with classical codes which have certain properties. Okay, so certain special properties. So we'll be looking at that next time. I will also prove to you that if S always has size 2 to the something, because the generators, as we saw before, if your generators are n1 up until nnk, then, and they're all got, recall always mi squared is always equal to 1 to the identity. So, and then they're commuting. So the subgroup that they generate is just taking the subset of them. Yeah. And so that's always 2 to the n minus k. If you have n minus k generators, and I will prove to you that the dimension of Q of S is equal to 2 to the k. Okay, so I will do that with my own very own proof, and not one Nielsen triangle, which is dependent on the going to the classical code and playing over there. But you don't need to. So we will do that quite simply, and then we'll do the binary codes, some more examples, and finally we will do fault tolerant quantum computation. Yes, so how to actually build circuits in a fault tolerant way to be able to deal with the noise. Okay, so we've got the theory and the actual. Okay, we're going to encode it onto these logical bits, but then how should we build our circuits? Okay, so I think I'll leave it there for today. I've made a right mess. If you could see, there is ink everywhere. So I'm going to clear that. I'm going to stop recording.